Hey, good morning, AP Stats. Unit 3, Packet 3. So we're still on the unit about collecting data, and today we're going to be talking about designing experiments. So previously we focused on observational studies, right? And we know the main difference between an observational study and an experiment is actually imposing treatment, right? When you have an observational study, you're just recording the data that you see. You're not actually imposing treatments to different groups. And so you cannot conclude any causation with an observational study because you have lurking variables that could confound the results. So designing experiments is extremely important because this is where we can actually draw the cause and effect conclusion if we do the experiment right. All right, so our learning objectives. Describe the placebo effect and the purpose of blinding in an experiment. Describe how to randomly assign treatments in an experiment using slips of paper, technology, or a table of random digits, which we already started with Packet 2, right? The table of random digits. Explain the purpose of comparison, random assignment, control, and replication in an experiment. So these are actually your big 4 pieces of an experiment: comparison, random assignment, control, and replication. All right. We're starting off strong, and I want you to read my experiment idea, pause the video, and come up with some problems with my plan. I know, your first thought is, you can't do anything wrong, Miss Lucas, but I can. So I need you to come up with some problems with my plan. So go ahead and pause the video, write down whatever you think could be an issue with what I have set up with my experiment. Okay. So let's see what some problems that I came up with, and you could have had different problems than me. So if you have other issues that I don't address in this video, please ask Ms. King about them. All right, so number 1, what if the sugar in the drinks was actually causing the increase in heart rate instead of the caffeine? So we're going to say sugar is a lurking variable, right? Because sugar can increase your heart rate. So if I'm trying to study the effect of caffeine, then sugar would be a lurking variable. And before I go any further, I should have done this in the first place. Let's go ahead and label our explanatory and our response variable. All right, explanatory is caffeine, and our response is heart rate. So I'm trying to see if caffeine has an effect on heart rate, right? So sugar messes with my results there. All right, number 2. What if I have some students with high caffeine tolerance? I know when I was in high school, my dad let me drink coffee. I thought I was super cool. So I drank coffee in the mornings to help me get up. So if I'm already used to caffeine, don't you think the caffeine would have less an effect on my heart rate than a student who hasn't had caffeine in the form of coffee? So students with high caffeine tolerance could mess with your results, right? Number 3, no control group. I'm not able to compare the caffeine to people that don't have caffeine, right? So comparison is important in experiments because I'm able to actually analyze the results of the explanatory variable and then a group without the explanatory variable, right? So I can actually see the response based on the explanatory variable. So there's no control group, so I cannot compare results. All right, number 4, possible placebo effect. All right, so when I say placebo effect, what I mean is that if you know that I'm doing an experiment and I'm studying the effects of caffeine on heart rate, and I actually drink some Coca-Cola, in my mind, I'm going to think, wow, this should affect my heart rate. And so my heart rate might actually go up because I'm thinking it, right? Well, later in the video, we'll actually watch a video on the placebo effect that will make more sense. All right, so possible placebo effect. Okay, so now that we've got all these listed, again, if you have anything else, please share with Ms. King and discuss with her in your class. All right, so Go back up to your list in number 1 and propose a solution to each problem. All right, so let's see, with sugar as a lurking variable. So what I need to do is control for sugar as a lurking variable. And I'll talk about what that means in a second. What control means is the same for both groups, right? Same for the control group, same for the explanatory treatment group. So I'll talk about that in a second when I talk about number 3, no control group. But right now we need to know that the sugar has to be the same amount for both groups. All right, number 2, students with high caffeine tolerance. So if I've got a class, I probably have maybe 4 or 5 students in this class with high caffeine tolerance. If I do random assignment to the control group and the treatment group, about half of the students with high caffeine tolerance should be in one group and half of them should be in the other group, right? So they receive both the control and the treatment. So I have roughly equivalent groups taking the control and taking the treatment. So then it won't mess with my results, right? What if randomly all of my students with high caffeine tolerance were in my treatment group? And then I'm like, wait, caffeine does not really have that much of an effect on heart rate, but it's only because all of my students in that group have high caffeine tolerance. If I split them up, randomly assign them to both groups, then that takes away that lurking variable. All right, number 3, no control group, can't compare the results. Add a control group. That does not receive caffeine. And then you can measure their heart rate. And you can analyze the explanatory and the response variable for each group, and you can see if the explanatory actually does have an effect on the response. So you're adding a control group that does not receive caffeine. That word not is really important. I can't believe I missed it. All right, number 4, possible placebo effect. So you know the people that are receiving the Coca-Cola are like, oh, well, I'm the one whose heart rate should go up, so maybe my heart rate should go up, right? So what we should do is give caffeine-free Coca-Cola to the control group. Be sure to cover the labels. That way the students don't know if they're getting the caffeine or if they're not getting the caffeine, and it also helps me control for the sugar content, right? So the sugar should be the same in both the caffeine-free Coca-Cola and the regular Coca-Cola. So if the sugar amount is the same, it helps me isolate the effect of the caffeine. This way, both sets of students don't know if they're getting caffeine or not, so it controls for the placebo effect, right? All right, design an experiment to test the effect that caffeine has on heart rate. All right, so what we're going to do here is a completely randomized design. All right, so a completely randomized design outline has certain things in it. Number 1, we always start with our sample size. So let's say we have 100 students here. And it doesn't tell us in here, or my plan doesn't tell you in here what it should be, so I'm just saying 100 students. All right, after I have my sample, my next step is always random assignment. I need roughly equivalent groups in my treatment group and my control group in order to control for lurking variables. So random assignment is key. If I don't have random assignment, then my experiment is not set up properly and I cannot draw a cause and effect conclusion. All right, so once I have random assignment, I randomly assign students into group 1 and group 2. So I should have 50 people in both. And how would I actually do random assignment? I could use a random number generator. Oh my gosh, generator. Or a random number table. And I could number people 001 to 100, right? And then use the random number generator or random number table to assign 50 to group 1 and 50 to group 2. All right, we'll say group 1 is the treatment group that gets the caffeine. And number 2 is the control group that gets the placebo, which is no caffeine, right? Now, once I get the results, I'm going to compare heart rate. So I compare the heart rates to see if the explanatory variable accounts for any change in the response variable, right? That's the whole purpose of designing the experiment, to see if caffeine has an effect on heart rate. So this is a completely randomized design that we'll do later in the packet. We'll do the same thing, but you always start off with sample size, random assignment, and this down here is just extra. You don't need this as part of the completely randomized design. I was just getting your brain working on how you actually could do random assignment. After that, you're assigning to 2 groups, and you want the groups to be roughly equivalent, right? So 50 and 50, and then you'll have a treatment group and a control group in order to compare results. All right, so let's actually start talking about the 4 main components, and I'm pointing at something you can't even see, the 4 main components of an experiment. So turn the page over. All right, so number 1, comparison. You have to use a design that compares 2 or more treatments, and one of those treatments could be a control group, right? You could have more than one treatment to compare against a control group. So you're going to use a design that actually compares, or else you have no idea if the explanatory variable had an effect or not, right? It could be due to another variable like sugar in our caffeine example. All right, random assignment. You're going to use chance to assign experimental units. And what are the experimental units? In our caffeine study, it was people. We were assigning people to treatments. Doing so creates roughly equivalent groups, right? So if I have lurking variables like maybe gender, maybe caffeine has different effect on women than it does men. Well, I should be able to have the same amount of women and men in each group so that it controls for that variable, right? So all I want to see is the change in the response variable that's due to the explanatory variable. So I have to have a random assignment to create roughly equivalent groups. That way it balances the effect of other variables among the treatment groups. All right, control. Keeping other variables the same for all groups, especially variables that are likely to affect the response variable. So my example here was sugar, right? In my caffeine experiment, if I had one group that had caffeine-free, no sugar, and the other group had sugar and caffeine, I'm not able to tell if the response was due to the sugar or the caffeine. So I need to keep the sugar the same in both the treatment and the control group. So control helps avoid confounding and reduces variability in the response variable. So I'm keeping all other variables the same. All right, when you think replication, I want you to think sample size. So basically, replication is saying that the results of my experiment are not a fluke, okay? I use enough experimental units, and again, people, right, in my example, in each group so that any differences in the effect of treatment can be distinguished from chance differences. When we say chance differences, we're saying flukes, right, between the groups. So basically, replication is saying, can I do this experiment over and over again and get the same results? Because if I can't, then I cannot say that the explanatory variable has any effect on the response variable. All right, go ahead and catch me on the next video.